Thank you very much, and thanks a lot for the invitation to this very nice and interesting place. I want to tell a story about the development of a particular topic in representation theory. I want to start out with a special case. I want to consider the general linear group on a finite dimensional vector space over some field. Let's agree that my field will always be algebraically closed. It will also have positive characteristic. So I may say a few words about characteristic 0, but almost everything will be positive characteristic. What I want to discuss then is I'll try to say something about the reducible representations of this group. So let's identify this with GLNK. N being the dimension of the vector space, and let's put T equal to the diagonal matrices in G, and then I will denote by X the character group, so the homomorphism from this group into the one-dimensional multiplicative group. And inside there, I'll take the dominant weight. So in this particular case, one of the important characters, elements of X, is the epsilon I, where epsilon I takes such an element in capital T into the i's diagonal entry. So this is the what I'll call epsilon I, and then in fact X is just the set span of this epsilon 1 up to epsilon n. So any element in X is a set linear combination of the epsilon i's, and the X plus will be then the set of, say, write it something like this. And to be dominant means that lambda 1 is bigger than or equal to lambda 2, and so on, bigger than or equal to lambda n. So if you like, you can also think of these as partitions of a certain number. So the partition of the sum here. The only thing is you don't require this lambda n to be positive. It can be anything, actually. So the reason I want to have this notation on the board is that whenever I have a lambda in X plus, maybe I'll actually put this on the next board. So if lambda is in X plus, I have several modules attached to lambda. One I'll call delta lambda, and another one I'll call naphtha lambda. So this delta lambda is what's known as the Laval module. For G, with highest weight lambda, and this one is the dual Laval module. And if we were in characteristic 0, these would be isomorphic, and they would be irreducible. And when lambda runs through the X plus, they will produce us all finite dimensional irreducible module. If you give me an irreducible module for DLN in characteristic 0, it's isomorphic to this module. So these are classical and very well studied and well known objects, but now we are in characteristic P, and these are usually not isomorphic and they are not irreducible. However, there is this guy always have a unique irreducible quotient, which also sits as the unique irreducible submodule of the nabla. So this is actually the reason for the notation here. This has a pointed top here because there is a unique simple top. This has a unique simple bottom, so it's sharp on the downside. Anyway, if you perform this, there is up to isomorphism only one map, which I'll call C lambda, from delta lambda into here, up to a constant. This is the unique non-zero homomorphism, and it's actually this composite here. So it will take top to bottom over here. All right. So so now it turns out that the set of L lambda, where lambda runs through x plus, that's the simple modules, the irreducible modules for our G. And the question I want to address is, or the first question at least, and the main one is the question, what is the dimension of this guy? Or if I want to be more sophisticated, I can ask for the character of L of lambda. So the character counts all the weight multiplicities, but let me not worry about this. Let's just focus on this one. It's a very natural question. You have a group. Can you find the dimension of all its irreducible modules? And the problem is that this is really, really hard. Again, if you were in characteristic 0, you have a beautiful answer. I told you that in this case, everything up this triangle collapses. There's just one module there, the one on the same layer, all isomorphic. And the dimension of this one is given by Wahl's character formula. One reason for the name Wahl module is that it still has the delta lambda and the nabla lambda. They both have characters equal to the Wahl character. And they have both dimensions equal to the Wahl dimension, given by the Wahl dimension formula. But now what is the simple quotient or the simple submodule? That's the question, and that turns out to be a very hard problem. So before I say more about this, let me address another question, which so I think this is typical for mathematicians. When we see a problem and it turns out it's very hard and we can't really solve it, well, we reformulate and find another question which we may be able to solve. I should just say at the outset that in this case the second question I'll actually ask is even harder than this one. So it's not just to get away with an easier question. I want to say a little bit about tilting modules. So I don't know if this may not be a familiar concept. So let me give a definition. Suppose I have a finite dimensional G module. I call it tilting. If it has two sorts of filtrations, so if there exists one filtration of G submodules, say starting in 0 and all the way up to say fr, which is the whole thing, q, such that the sections here are certain deltas. So it's called tilting if it has one such filtration and another one, say f0 prime, f1 prime, and so on. It turns out that it will have the same length always, but this time the quotients are Napler, say mu I. So this is a requirement to be tilting. If some of you are working in finite dimensional algebra theory or something, you may object that this is not the right definition. It should maybe be called partially tilting, but it has been now a tradition since Duncan introduced this name 25 years ago now. In algebraic group theory, we call this tilting. So let's agree that this is what it means to be tilting in our world. And one of the facts that I'll be using is that when again I give myself a dominant weight, then there exists a unique opto-isomorphism d module T lambda. So this is an indecomposable tilting module with highest weight lambda. And in addition, this gives all indecomposable tiltings. Right, so I just brutally introduced this definition and gave you the first fundamental fact about it. It's clear that now if you have any tilting module, well, it will decompose into indecomposable summands. And each indecomposable summand will look like one of these T lambdas. So we can now put T lambda into the picture up here. So I'll put it down here because it turns out that, remember, this does have a delta filtration. This sort of filtration here is called a delta filtration, this one a Napler filtration. It does have a delta filtration, and this delta filtration in fact does have to start with delta lambda. And likewise it has a Napler filtration, and for weight reasons there will be a surjection from T lambda onto there. And the reason I wanted to put it into the picture is that, that this diagram still commutes. The inclusion here, followed by the surjection, is this unique non-zero map from delta to Napler. And now the second question I want to ask is, what is the dimension of T lambda? So again, if the characteristic can be 0, I have not told you anything new at all. This T lambda would just be equal to delta lambda, because delta lambda certainly has a delta filtration. In that case, it also has a Napler filtration because these two modules are isomorphic, so clearly this will do the same. So the whole diagram are not 4 modules, but just one module. And these questions are completely the same, and the answer is well known, given by Laval's dimension formula. But not so in characteristic P. And one of the big obstacles in the theory is that, as I promised, this second question is in fact harder than this one. One of the things I will say more about in a little while is that in fact Q2 does imply Q1, at least for most primes. It's not yet known for very small primes, but sort of the general philosophy is that this the answer of Q2 will imply Q1, whereas the answer the other way around is not certainly not known and probably not true. So just to tell you how far away we were from an answer to this question is, I did start with this group. Everything I have said will work for any reductive group, so I could actually here replace now G by any reductive group. G and take a maximal torus here and do the corresponding thing. So I've tried to set up everything so it works in general. But I invite you to think about this group, because if we could answer these two questions for these groups, that would already be a very big step. And to illustrate how big the step would be is that if we go back 3 years, then the answer to Q1 for this group would be known if the dimension is less than 6. The answer to this question is known when the dimension is 2, but for dimension 3, it's completely unknown. So this also illustrates, I mean, take GL3, a rather small group, I would say, and you would think, well, you should be able to hammer out this, the answer to this question, but not so. Even though you do have a solution to the first question in that case. So it does help you produce the first few T lambdas, but not all of them. And this I will also illustrate a bit later. So while I still have the board here, let me put in some notation. So I want to count the number of times a given delta lambda occurs in the filtration there. So Q is still my tilting module, so I can count the number of i's such that lambda I is equal to lambda. Maybe the same lambda occurs 7 times in the sequence there, and it does turn out that I will maybe also need the notation here, but it will mean just the same thing. This is counting the number of j's down here, such that mu I is equal to lambda, but this will be the same number for some very good reasons, which I don't want to get into. So this is my notation, which counts how many times it occurs. I will also need the notation Q T lambda. So this is the number of times T lambda occurs as a summand. In Q. Remember that Q does decompose into a direct sum of various indecomposables, so I just count how many times does my favorite T lambda occur, and I denote it by this number. So now I can write Q is the big direct sum, or lambda in X plus, and then T lambda that many times. Of course, almost all of these are 0. We are talking about finite dimensional modules, so it is a finite direct sum. So this is one piece of notation that I will need in the following. The second one, second piece of notation is if I have any module and I want to talk about the composition factor multiplicity, I'll denote it like this. So this is the composition factor multiplicity. The number of times this irreducible module occurs as a composition factor of m. So I put these down for for several reasons. I'm going to need them later on, but I could now reformulate question 1, because as I told you, the delta lambdas we know all about. We know their character formula given by Laval's formula. So it turns out that to find the dimension of the irreducibles will be equivalent to finding these numbers. Find the composition factor multiplicity of L mu in all of the delta lambdas. Likewise, the question 2 here is equivalent to finding the numbers T lambda. I decided to write round bracket here. If you can find these numbers for all mu, then you have of course the knowledge you need of T lambda. So question 2 is also a question of finding these numbers. And let me go on with this and tell you at least the first one is a very classical fact. So there is something called the Steinberg tensor product theorem. It's due to Steinberg and it dates back to 1963, I believe, at least the 1960s. So that's why I say it's classical. It says that if I take my lambda in x plus, I can cut the work of finding the dimension of L lambda into smaller parts. I can take my lambda and write as lambda naught plus p lambda 1, where lambda naught belongs to x1. x1 is the set of restricted elements, so let's say it's the mu's in x plus, such that mu I minus 1 is less than p for all I. So I'm still now referring to the example I have just erased of DLV, where the dominant weights are, so mu here is sigma mu I epsilon I, and what I'm asking is that the steps you take from mu I minus 1 to mu I is less than p. So this is the set of what's usually called restricted weights. And I mean, you can certainly then write any lambda like this, where lambda 1 is then just some other element of x plus. So you can uniquely write lambda like this. This is just a sort of a residue division, if you like. So you do this with lambda, and then Steinberg tells us that L lambda is isomorphic to L lambda naught, tensored by something denoted L lambda 1 with an upper bracket 1. What do I mean by this second module? So it's clear that I do have a simple module associated with lambda naught. I have another one associated with lambda 1, and I can take the tensor product. But I want to twist the action on the second tensor factor. So this upper means twist by the Frobenius. Frobenius is a map from G to G. The first Frobenius, if you like, the one that on a matrix like I'm using as my main example, it just raises each entry to the piece power. Of course, you could raise to any power here, and you would get higher Frobenius, and you could put in some bigger number. But I'll stick with number 1 here. So this is the Steinberg tensor product theorem, which is a very useful one, because if I have found the dimension of all these guys, the ones in x1, and that is a finite, at least if I pass to SLN, it will be a finite set. And once I have done this, I know that my first part here, then I look at the second part. If I'm lucky, lambda 1 also belongs to x1, and I'm done. If not, well, I just take lambda 1 and write it in this form and use it the same formula again. So in the end, I'll get L lambda as maybe a very long, but still a finite tensor product of modules, all of which comes from this with highest weight inside this. So if I can solve question 1 for this set, then I have a complete solution. So this will make this problem finite. And this is actually one big difference to the second question. There's actually no such analog of Q2, no complete such analog. Right. So as I pointed out, this has been known for many years, and still one wasn't able to decide the answer in this finite looking set. So then came an important development in '79, where David Kasten and George Lustig came up with some intriguing polynomials. So Kasten and Lustig in 1979, they came up with what has become known as Kasten-Lustig polynomials. So these are polynomials associated with Coxeter groups. So whenever I have two elements x and y in a Coxeter group W, they construct for me a polynomial denoted pxy, like Kasten-Lustig polynomial associated to this pair. So for instance, W could be the symmetric group on n letters, say, and it could also be the affine Weyl group corresponding to this. And this is relevant for the following reason. So there's a famous conjecture by Lustig, related very much, well, giving a suggestion for the answer to Q1. So this was put forward by Lustig in the same year. He says that if I look at these numbers, or rather I turn the problem around, I take and reverse the formula. So what do I mean by this? Well, I mean this will sort of write delta lambda as a sum of L mu's. Because of this highest weight business, it's very easy to see that the matrix here you come up with will be invertible. So these are the inverse matrices. Now these are now integers, not necessarily positive. These numbers, so well, maybe I should make this precise. What I'm saying is that you can write the module virtually as a sum where you get these numbers p mu lambda, certain numbers times delta lambda. So if you like, I want to find the character of this module. The character of this module I can certainly write as a set linear combination of Weil characters. The Weil characters form a basis for this business, and so there will be some unique numbers, numbers here, and these are the ones I also sometimes denote like this. So the unique number you need to put in here is denoted like this, and then Lustig conjectured that if lambda is in x1, then p mu lambda is, well, I'm not going to be very precise here. There will be two elements, x mu and x lambda, from a particular Coxeter group, such that these integers here that you are after are given as the values at one of the Kasten-Lustig polynomials. And the Kasten-Lustig polynomials we need here are the ones associated to the affine Weil group. So in the GLN case I was talking about, the Weil group itself would be the symmetric group on n letters. Now you take the corresponding affine 1, which I denote by WP, which is a semi-direct product of Sn, the symmetric group, and then the lattice x, or p times x. So this is in general something like this, x, p times x. That's why I put the p on here. As a group, it doesn't matter, but for the notation, it makes sense. And I'm not precise here. There is a precise recipe which Lustig does describe for how to associate an element x mu to mu and x lambda to lambda. But I only want to tell you sort of the moral of this conjecture. It tells you that you can solve question 1 if you can compute these numbers. And these numbers are indeed computable because they, in their paper from '79, they give an algorithm for how to obtain the polynomials themselves, and you can certainly evaluate these polynomials at 1. Well, it's still in any given case, if you take the symmetric group on 100 letters, you will certainly you'll have some work to do, but in principle you can do it. There is one thing which I should have mentioned here when I stated the conjecture. He requires p to be bigger than 2n minus 2. In general, 2 times the Coxeter number minus 2. So there are some exceptions for the small primes, which he was aware of. This conjecture, of course, made a lot of people, including myself, look at this problem again and tried now to verify or disprove the conjecture. Because this was the first time where there was, people had been looking at some few examples, low-rank cases, and they had computed these for some of these groups. But there wasn't any real pattern that people could discover until Lustig came up with this conjecture. So there was then a big, a lot of efforts putting into proving this conjecture. And one of the, I want to mention one of the results on the way because I was involved myself. That's at least one excuse for mentioning. Together with Janssen and Circle, back in 1994, we proved that if P is very large, then the Lustig conjecture is true. So I call this conjecture here, this conjecture here I call the Lustig conjecture, LC. And LC is true when P is very large. What does it mean for P to be very large? Well, let me state it again for GLN, which is my favorite example. It means that there exists a number which will depend on n, but on nothing else, such that if P is bigger than this number, then LC is true. We couldn't, although we struggled several months to compute this number. How big has P to be before this is true? We had to give up in the end, and we wrote our paper, a 300-page paper, which built on. So I should say this builds on several papers by Kasten and Lustig, and on another couple of papers by Kashiwara and Tanizaki. So the whole story to verify the sort of morally Lustig's conjecture does involve quite some work. It's not trivial. Of course, it's not very satisfying because suppose you now take DL6 and you ask, well, for how many primes do we actually know the answer? We can't tell you. We just know that after a certain number, then for all primes below about this number, the Lustig is right. And as I said, we struggled, and several other people looked at well, how to bound this number. And I should mention that Peter Fiebig, he came up with a bound. For DL6, his bound is something like 10 to the 40. So it's an enormous bound. It's probably much too huge, but anyway, it was a concrete bound, and not just for DL6, but for any reductive group, he could give such a bound, which depended on the order of the Weyl group and some other factors, which I won't get into.
So I missed it. 10 to the 40. You said
yes, for DL6, something like 10 to the 40. So it's enormous. And I mean, you're doing some estimate, maybe you can cut it into half or maybe even divide it by 10 to the 12, but still it will be huge. And this was the sad story until 2013, when I went to a conference in China where George Williamson told me when I met him, I have a surprise for you in my lecture. And certainly, and he didn't want to tell me what the surprise was. I sort of had a feeling that he would tell me either he had solved Lustig's conjecture or he had dissolved it. And the last thing was correct. What Williamson said is that let me still stick to this example. This was actually the one she was using at the time. Maybe I can just say the moral of his point was that LC is false unless P is very large. Exactly what he meant was the following: that if you give him a polynomial, suppose f is some polynomial in one variable, then for all n, there exists p bigger than f of n, such that LC is false in characteristic P, in that characteristic. So how about taking f to be t to 1 million? Then it says that there will be primes bigger than 1 million for which Lustig's conjecture fails. So what he did was he constructed for a sequence of primes which kept growing, and for the group DLN he could find particular lambdas. So he produced specific lambdas where this conjecture fails. So this certainly made Jansen, Circle, and myself feel a little bit better, because this was one good reason why we had not been able to find a specific bound, or we thought we were stupid, and that well, at least first we thought we were stupid, like we could remove this completely, but no such luck, and now we certainly know that it's impossible. All right. So, so this was the story as of 5 years ago. So I want to then pass on quickly, because there has been an enormous development in the last 2 or 3 years. So let me make sure I have something else to say, but let me make sure I do get to tell you this, that in a young French mathematician, Ritchie, and Georgia Williamson, they put on the archives in December 15 they put on they solved Q2 for G equal to DLN when P is bigger than N. Okay, so one of the things I still hope to have a little time to say something about is this implication here. But let's, for the moment, believe that if we can solve Q2, then we can also solve Q1. So at least they announce now that this is fine if P is bigger than N. Now, this is still not quite satisfactory because you really want to solve it for all DLV. In particular, for some applications to the symmetric group, it's very important that you do not have any restrictions on P with respect to N. But still, this was a great advance in here. It was the first time where you have a solution, any sort of solution for this harder question, Q2. And it didn't last too long. When was this? This was in 2017. Ben Elias plus Losef. Losef is, what's his first initial? That's an Ivan, yes. Yes, Ivan. Okay, so they got rid of this restriction. So all DLN. Right. So as I said, even though this certainly is much better than saying P very large, it gives a very explicit and quite low bound. But they were able to remove it completely, so that's perfect. And this was in the end put on the archives in January 17, and in June 78 there was a new development by Pramod Archyat, Murikani, Esmaki, Kami, S. Ritchie, same guy as up there, and Jody Williamson. So this was June 17. So they solved again Q2 for all D when P is bigger than H. H is the constant number. So in the case of type A, in the case of DLN, this is the same condition as in the first work there, but now they made it work for all other reductive algebraic groups. So that indeed now we have a solution of Q2. There are a few small primes still to worry about, so I'm happy to see some young people here who can, in the next few years, tell us what happens for small primes when you look at type E8 or something. So let me not say more about this. This is a fantastic new development. Again, I mean, I should probably say that. Some of the techniques involved are instead of the Hecke algebra, which has plays a role in the Kastanlustig theory. There's a Hecke category which they have sort of invented, where they can use what they call the diagrammatics. So this is a category where the objects sort of corresponds to the usual objects in the Hecke algebra, but then where there are some morphisms which they can picture by drawing diagrams, and there are some relations that these diagrams satisfy, and so they can really handle many things that way. They can come up with something like what they call a p-canonical basis. For these endomorphism things, and then they are able, using this to produce an answer. And this p-canonical basis is called so because it's very much related to the Kastanlustig theory. A few years later, Lustig came up with what he called canonical bases associated with the Kastanistic polynomials, and Kashiwara has another version where he talks about crystals, canonical crystals and so on, which does play a big role in this sort of representation theory where the characteristic is not prime, but where you're dealing with what's called the category O. So they are in some sense imitating this, and I should also mention the name here because there are some circle bimodules which play a big role. But as I said, if you really want to look at this, you should look at least the papers on the archives by these people, and some of the references they give. So there's a big story behind this. It's not an easy solution, but it's the first time that we do have any sort of solution of Q2. It will involve an algorithm which is much worse than the one I talked about before, where you had to compute these Kastanistic polynomials. At least there you have a decent algorithm. In their case, you have to work much harder. So there's still work to do, I think, to simplify or to find some better ways of describing the solution. But the solution is there. So before I end. I want to address the question the problem I mentioned of passing from Q2 to Q1, because in some sense I was very surprised to see that the solution would come this way around. I thought that one would certainly have to first solve Q1 before having any hope of producing a solution to Q2. But now it has turned upside down. So I did make an observation already several years ago now that Q2 implies Q1 if, so again there's a sort of a problem with small primes. If P is bigger than 2h minus 2, then this is a fact. And it's quite an easy observation, actually, once you know a few things about tilting modules. So I want to put D1 equal to the kernel of my Frobenius homomorphism. Remember I had this Frobenius from G to D, which in the case of DLN raises interest to the P's power. This has a kernel. Well, you'll say this kernel is trivial, right? Because if a number to the P's power is 0 or 1, well, not that many solutions. So, but what I want to say here is this is scheme theoretic. So it's what's called an infinitesimal group. Or a field, it has just one point. But over a more complicated rings, it may have many points. And it has an interesting representation theory. So again, the elements of X1 play a crucial role. Already back in 1961, I believe, Curtis proved this statement. If you take an L lambda where lambda comes from X1, then and restrict it to D1, you will get an irreducible module for D1. And again, you can add that this gives you all irreducible D1 modules. So I'm really here talking about modules in the sense of algebraic group schemes, and you get a good classification. You have one for each lambda. And you take the module for the group itself, and you just restrict it to D1. Right? One advantage of working with D1 instead of G itself is that you have projective modules. So let me put Q1 lambda equal to the projective cover of L lambda. And now here I'm talking G1 modules. Now it was this has been looked at for many years, and of course in any sort of decent representation theory to describe the simple modules, you can do if you can describe the projective covers. So it turns out that it's easier to deal with these. And now to make I'm cutting here some other developments which I cannot have time to, but Duncan conjectured in '92 that this Q1 lambda, in good cases at least, has something to do with tilting modules. He says Q1 lambda is a particular tilting module restricted to G1. So here lambda hat is, well, let me just write it down. I don't have time to get into the technicalities here, but let me just put out that there is a specific formula for how to find the right weight here. What you should do is then you should take the tilting module there, then you get Q1 lambda. So in fact this Q1 lambda has a D structure, namely this D module restricts to it. And here is where the snack comes in. He can only prove this if P is bigger than 2h minus 2. He conjectured that it's true for all P, but he could not, and no one else has been able to do much about this. So we'll still have to work with this assumption. Now you can see that if we have an answer for Q2, we know this module, so we know the projective modules here. Let me make just instead of introducing the full notation there, let me make a picture to illustrate what happens. If we work with a group, let me pass to SL just for convenience, SL3. So the dominant weights form a cone like this. So there are infinite many weights in X plus, all the integral points inside here. Now if you have a particular prime, then the first box here. So if you put the limits here where you move P steps away from the origin. By the way, the origin has to be minus rho. So you move P upside this line, and P steps up there, and you take the corresponding sort of diamond shape here. This is X1. And this similar thing will work for a general group. In this group it looks like this. Now I have been stupid and I have to move this. Because the point is that if you have a lambda here, the corresponding lambda hat is in the box sitting just above this smallest box. So here is a lambda hat, it's the mirror image in this point here of this. So lambda hat is somewhere up there. And what Duncan says is that if you take the tilting module, take all the tilting modules with highest weight in this box, this not the smallest box, but the one sitting on top of it. Solve Q2 just for this tiny part of the problem. Q2, which I have now erased, deals with all possible dominant weights. And there are infinitely many of those, and you cannot make the problem finite. But this finite part of the problem will be enough to determine the simple modules in X1. And as I have told you, this will prove the Q1. So that's how the connection goes between Q1 and Q2. Again, I should stress that there are certainly still work to be done there. And I think the biggest work is to, well, find out why why does this recipe that they give us, why does it work? Is it possible to reformulate part of it, or do some clever tricks so that it will be possible for humans to really work out the algorithmic answer? You can put it in their method into a computer, and they can compute a lot of things. But still, to do this by hand is almost impossible, even for SL3. So, thanks very much for your attention.
Any questions, remarks?
So, basically now we know that the heuristic conjecture is false, right, in general. So in which terms are these answers to the dimension questions obtained? So what kind of answer do you get?
Yes, first of all, I should say that Lustig was in the audience in China when Georgia Williamson announced his counterexamples. And when someone used the same words as you used, now that we know that Lustig is false, he objected. I'm not false, I'm morally correct, because for any group, not just a finite number of primes where there are problems. And I think, in some sense, he certainly deserves credit for coming up with a morally correct conjecture on a question which was impossible. Now that we can, we have a different version of another method which does produce for almost all primes the question. What we can do is we can for instance solve what I would call the corresponding question for symmetric groups. If you take a simple module for the group algebra of the symmetric group or my field K of characteristic P, it has been a big challenge to find the irreducible modules. But now there's a correspondence between symmetric groups and general linear groups. So now that we can handle all general linear groups, and notice that this is done, this means that we can also now find the dimension of all simple modules for these finite groups, which has been, as I said, one of the big open questions in that area. And well, there are several more things. I'll actually, in my second talk, I will come into some of the other applications. I'll touch upon them at least.
So about the algebras that replace the algebras behind heuristic conjecture, you will speak in your second talk?
No. Unfortunately, now this is a long story in itself, and my second talk will not focus on this, but I will come up with some applications of the solution of Q2, not really the methods of proof.
Any other questions? Okay, so let's thank the speaker again.